Welcome to Nuclear Physics. In this topic, we will explore the structure of atoms, radioactive decay, nuclear reactions, and the applications of nuclear science. We will learn how changes inside the nucleus can release large amounts of energy and produce radiation. A-level nuclear physics specification, overview, and context. Nuclear physics focuses on understanding the structure, behavior, and transformations of atomic nuclei, as well as the applications and implications of nuclear processes. This topic includes isotopes, nuclear forces, radioactive decay, and mass-energy equivalence. AQA places strong emphasis on both conceptual understanding and quantitative problem-solving, requiring students to apply equations such as A equals N, N equals Ne, and E equals mc squared. Structure of the nucleus, protons, neutrons, and isotopes, nuclide notation and nuclear equations. The atomic nucleus is a compact region at the center of an atom containing protons and neutrons, collectively known as nucleons. Protons carry a positive charge of plus 1.6 times 10 to the power of 1c, while neutrons are electrically neutral. The number of protons in a nucleus defines the atomic number, Z, which uniquely identifies the element. Isotopes are atoms of the same element that have the same atomic number but different numbers of neutrons. As a result, isotopes have the same chemical properties but different nuclear properties, such as stability and likelihood of radioactive decay. The nucleus occupies only a tiny fraction of an atom's volume but contains almost all of its mass. Typical nuclear radii are of the order of 10 to the power of 1 m, compared with atomic radii of about 10 to the power of 1 m. This extreme concentration of mass leads to very high nuclear densities. Nuclide notation provides a concise and information-rich way of representing atomic nuclei. A nuclide is written in the form _ZX, where X is the chemical symbol, A is the mass number, and Z is the atomic number. From this notation, the number of neutrons, N, can be calculated using N equals AZ. Nuclear equations use nuclide notation to show changes that occur during radioactive decay or nuclear reactions. In alpha decay, the nucleus emits an alpha particle, which is equivalent to a helium-4 nucleus, He. As a result, the parent nucleus loses 2 protons and 2 neutrons, so its mass number decreases by 4 and its atomic number decreases by 2. The strong nuclear force and nuclear stability, nuclear radius, density, and experimental evidence. The strong nuclear force is the fundamental interaction responsible for holding the nucleus together, overcoming the electrostatic repulsion between positively charged protons. This force acts between all nucleons, proton-proton, proton-neutron, and neutron-neutron, and is extremely strong at very short distances. Its range is limited to about 3 femtometers, 3 times 10 to the power of 1 m, beyond which it becomes negligible. This short range explains why the force is effective within the nucleus but has no observable effect at atomic or macroscopic scales. At distances slightly greater than about 0.5 fm, the strong nuclear force is attractive, pulling nucleons together and providing nuclear stability. However, at very small separations, it becomes repulsive, preventing the nucleus from collapsing into an even denser state. Experimental evidence shows that nuclear radius depends on the number of nucleons in the nucleus, leading to the relationship R equals Ra to the power of 1 cubed, where R is the nuclear radius, A is the mass number, and R is a constant approximately equal to 1.2 times 10 to the power of 1 m. It implies that nuclear volume is proportional to A, since volume depends on R cubed, and therefore that nuclear density is approximately constant for all nuclei. The constant nuclear density is a significant result because it supports the idea that nuclei are made of tightly packed nucleons with very little empty space. This contrasts sharply with atoms, which are mostly empty space. Typical nuclear densities are of the order of 10 to the power of 1 kilogram m cubed, vastly greater than any everyday material. Radioactive decay as a random and spontaneous process, alpha decay, nature, properties, and equations, beta-minus decay and the role of the neutrino, gamma radiation, and nuclear energy levels. Radioactive decay is a fundamental nuclear process in which an unstable nucleus transforms into a more stable configuration by emitting radiation. Random means that it is impossible to predict exactly when a particular nucleus will decay, even if it has existed for a long time. Spontaneous means that decay is not triggered by external factors such as temperature, pressure, or chemical state. Although individual decay events are unpredictable, large numbers of identical nuclei show predictable statistical behavior. This leads to well-defined concepts such as activity, half-life, and decay constant. Alpha decay occurs when an unstable nucleus emits an alpha particle, which consists of 2 protons and 2 neutrons bound together, identical to a helium-4 nucleus. This process typically occurs in heavy nuclei, such as uranium or radium, where the strong nuclear force is insufficient to overcome electrostatic repulsion across the entire nucleus. In alpha decay, the parent nucleus loses 2 protons and 2 neutrons, so its mass number decreases by 4 and its atomic number decreases by 2. Alpha particles are relatively massive and carry a +2 charge, which makes them highly ionizing. As they pass through matter, they interact strongly with atoms, removing electrons and creating ions. However, because they lose energy rapidly, alpha particles have very low penetrating power. They can be stopped by a sheet of paper, a few centimeters of air, or the outer layer of human skin. Beta- decay is a radioactive process that occurs in nuclei with an excess of neutrons. In this decay mode, a neutron inside the nucleus transforms into a proton, emitting an electron, the beta particle, and an antineutrino. The mass number of the nucleus remains unchanged because the total number of nucleons is conserved, but the atomic number increases by 1 due to the formation of an additional proton. Beta particles are much less massive than alpha particles and carry a single negative charge. As a result, they are less strongly ionizing but have greater penetrating power. Beta radiation can pass through paper but is typically stopped by a few millimeters of aluminium. Gamma radiation is a form of electromagnetic radiation emitted by an excited nucleus as it transitions to a lower energy state. Unlike alpha and beta decay, gamma emission does not change the number of protons or neutrons in the nucleus, so both the atomic number and mass number remain unchanged. Gamma rays are often emitted following alpha or beta decay, when the daughter nucleus is left in an excited state with excess energy. Gamma photons have very high energy and no mass or charge, which gives them low ionizing power but very high penetrating ability. They can pass through paper and aluminium and require dense materials such as thick lead or concrete for effective shielding. Activity, decay constant, and the equation A equals N, half-life and exponential decay curves and logarithmic interpretation. Activity is a measure of how quickly a radioactive source decays and is defined as the number of decays per unit time. In the SI system, activity is measured in becquerels, BQ, where 1 becquerel corresponds to 1 decay per second. The formula is A equals N, where A is the activity, lambda is the decay constant, and N is the number of undecayed nuclei present at that time. The decay constant, lambda, represents the probability per unit time that a given nucleus will decay. A larger decay constant indicates a more unstable nucleus that decays more rapidly. Importantly, lambda is a constant for a particular nuclide and is unaffected by external conditions. This reinforces the spontaneous nature of radioactive decay and distinguishes it from processes influenced by environmental factors. Half-life is defined as the time taken for the number of undecayed nuclei, or equivalently the activity of a radioactive sample, to reduce to half its initial value. It is a characteristic property of a particular isotope and is independent of the amount of substance present. Because radioactive decay is a random process, half-life emerges from statistical behavior across large numbers of nuclei. After one half-life, half the original nuclei remain. After 2 half-lives, 1/4 remain, and so on. This leads to an exponential decrease in N and A over time, described by the equations N equals NE and A equals AE. Half-life can be determined experimentally by measuring activity at regular time intervals and identifying the time taken for activity to halve. Radioactive decay curves show how activity or number of undecayed nuclei decreases with time. When plotted on standard linear axes, the decay curve has a characteristic exponential shape, falling steeply at first and then more gradually. On a decay curve, the half-life can be found by identifying the time taken for the activity to fall from a given value to half that value. Importantly, the half-life remains constant throughout the decay, regardless of when it is measured. This graphical method reinforces the idea that half-life is independent of the initial quantity of radioactive material. Mass defect, binding energy, and E equals mc squared, binding energy per nucleon and nuclear stability. Mass defect refers to the difference between the total mass of the individual nucleons that make up a nucleus and the actual mass of the nucleus itself. Experimental measurements show that a bound nucleus has a slightly smaller mass than the sum of the masses of its separate protons and neutrons. This missing mass has been converted into energy when the nucleus was formed, according to Einstein's equation E equals mc squared. The energy equivalent of the mass defect is known as the binding energy of the nucleus. Binding energy represents the energy required to completely separate a nucleus into its individual nucleons. A large binding energy indicates a stable nucleus, as a significant amount of energy would be needed to break it apart. Binding energy values are typically expressed in joules or megaelectronvolts, MeV. Binding energy per nucleon is obtained by dividing the total binding energy of a nucleus by its number of nucleons. This quantity provides a useful measure of nuclear stability, as it represents the average energy required to remove a nucleon from the nucleus. The binding energy per nucleon varies with mass number and shows a characteristic curve when plotted graphically. The binding energy per nucleon curve rises steeply for light nuclei, reaching a maximum of about 8.8 MeV per nucleon for iron-56 and nickel-62. These nuclei are among the most stable in the universe. Nuclear fission, chain reactions and reactors, nuclear fusion and energy production in stars, radiation risks, monitoring, and safety. Nuclear fission is a process in which a heavy nucleus, such as uranium-235, absorbs a neutron and splits into two smaller nuclei, releasing energy and additional neutrons. These emitted neutrons can go on to cause further fission events, leading to a chain reaction. In a nuclear reactor, the chain reaction is carefully controlled to release energy at a steady rate. Control rods made of materials such as boron absorb excess neutrons, while a moderator, often graphite or water, slows neutrons down to increase the likelihood of further fission. The energy released in fission is transferred as thermal energy, which is then used to produce electricity via conventional turbines. Nuclear fusion is the process by which light nuclei combine to form a heavier nucleus, releasing energy. In stars, fusion typically involves hydrogen nuclei combining to form helium through a series of reactions known as the proton-proton chain. Fusion releases vast amounts of energy because the resulting nucleus has a higher binding energy per nucleon than the original nuclei. Fusion requires extremely high temperatures and pressures to overcome the electrostatic repulsion between positively charged nuclei. In the core of the Sun, temperatures reach millions of Kelvin, providing nuclei with sufficient kinetic energy for fusion to occur. Radiation poses potential risks to living organisms because ionizing radiation can damage cells and DNA, increasing the likelihood of mutations and cancer. The severity of the risk depends on factors such as the type of radiation, the dose received, and whether the source is internal or external. In this topic, we have explored atomic structure, isotopes, radioactive decay, radiation types, half-life, and nuclear reactions. Understanding nuclear physics helps us explain how matter behaves at the smallest scale and how nuclear energy can be used. Thank you for watching.